So I've got a couple examples to work through before we lead into non-standard cells. Okay? Both of these examples are standard. So we have a standard lead dichromate cell. It's going to be a repeat or an example of seeing cell notation. I'll calculate the cell potential. That's old. And then we've got a second bit, which is new. What would happen if I change the reference? Hydrogen half cell is our zero voltage on our reduction potential table. But that was just picked by chemists. And we're going to look at what if the hydrogen wasn't the zero, the hydrogen half cell, what if the OA water was the reference? Okay. Now this is one of the outcomes of the course. You would expect something like this to show up in your test, and I expect something about the reference to show up on the diploma. So jumping back to the start, for a standard, okay, that word has a lot of meaning. I haven't dived as deeply as I'm about to go into it. When you see the word standard, that means you've got 1 mole per liter of the chemicals, and it's telling you you've got both sides of the half reaction. So even though this just said standard lead, it's meaning the whole lead half. Okay, and then when it talks about the dichromate, you've got the total dichromate half. Okay? Standard cells have both the left and the right-hand side in them. Okay? So this is a bit of a short form. They're not going lead ions and metal, they're just saying lead. Okay? So if we identify our 2 half reactions on a table, it talked about standard dichromate. So there's our dichromate. We've got all the chemicals in that half reaction. The other half reaction was the lead. Okay. And it's referring to a lead metal-based half reaction, not ion. So there's our lead as an Ra, but we've got the lead ions also. Okay. So we have a standard cell with everything in those 2 rows. So we're asked to write out the cell notation. So I'm going to kind of get out the layout. Okay. You have to start with the anode first and the cathode second. So I'm going to flip back to my cell notation. Anything standard voltaic, our table is our guide. Instead of writing, we're not going to use oxidation states. We're not going to write all the ions out. So we have half reactions based on dichromate and lead. The higher up half reaction will always have the strongest oxidizing agent, which is going to react at our cathode. The lower down half reaction, the chemical on the right, will have our strongest reducing agent, and that's going to react at our anode. It's always cathode is the higher one up. The anode, the Ra, will be the lower one down. Okay. And this really helps you get through voltaic cells quickly if you remember these patterns and structures. So we have to start with the anode first. So in cell notation, I'm starting with the lower half reaction, and then on the far right will be the cathode. That's just the ordering of cell notation. So lead first. Is there a solid in that half reaction? There was. Okay. The electrode has to be something solid you could actually connect your wires to. Okay. And we have that, elemental lead. Then we put any of the electrolytes. So we need lead ions. Okay. And that covers both sides of that lower half reaction, and we had a solid metal. Cathode electrolyte, then the cathode metal comes second. So now I'm looking at the top half reaction. Dichromate, acid, chromium-3, and water. So all the ions, we had dichromate. I'm going to need more room, so I'm going to take out that red vertical line. We're not H+. Now I'm not doing a count, I'm just doing a list. chromium 3+ ions. And then I'm not going to include water on my list. These are all listed as aqueous, so I'm done. Now you have to be careful. If water is one of the reactants or products, it may not be listed. It might be implied with one of the aqueous. So then I can put a vertical line, and then I need a solid that we can connect the wires to. But we didn't have a solid in the dichromate half reaction. So you'd have to think, oh, we have to use one of those inert electrodes, either platinum or carbon. And I'll use a carbon inert electrode to finish my cell notation. Okay. So we have a standard lead dichromate cell planned out. We did the cell notation, and I want to do the standard cell potential. Okay. You don't need half reactions. You don't need nets. All you need to do is look at your two half reactions. Okay. This is something on a multiple choice diploma style question you can get right from your table. I'm going to flip there in a second. We need the standard, that's the little circle, reduction potential of the OA. So that's going to be at the cathode minus the standard reduction potential of the RA. I'm just reminding you that's at the lower anode. Okay. So just don't start balancing. It's your default in chemistry. I'd normally say get an equation to start, but it's not necessary here. Reduction potential of the dichromate is 1.23 positive. The lead is negative 0.13. That's all you need to grab. So again, a lot of voltaic can be done without writing stuff down. We got to watch our signs. It's 1.23 volts positive. I'm going to switch to a different color for my subtraction. And then the reduction potential of the reducing agent was negative itself. So we end up with a subtract negative and then a negative number. So when you correctly do that math, you get a positive 1.36 volts. Voltaic cells should always be spontaneous. They should always be positive. The positive means this happens on its own. You connect it up, the electrons freely go from the anode to the cathode. So we've answered that. So that kind of ends the more review part. What about this? What would change if water as the OA was the reference? I'm going to flip to the table and give you a visual first. So we need water as an OA. So there's water as an oxidizing agent. We're being asked, what if that voltage, that negative 0.83, was the zero in the table and everything was rescaled off that? Okay. So we need to rescale all our numbers. Okay. How high up is the lead now? Okay. Before, it was below our reference, 0.13 below. Now it's above our reference. It's going to have a positive voltage relative to this lower zero. So there's a few ways to solve this. You can just sort of work the math out of what is the difference. How far up is negative 0.13 from negative 0.87. Okay. If you do like a formula, you don't get this, but to change the reference, you want to change the reduction potential reference, E naught cell, that's RED for reduction, new. You can take the E naught reduction that the table says, the old one in the table, and you can subtract the E naught reduction of the new reference. So take the number in the table, subtract the new reference, and you will rescale that, or you could rescale any of them. So that's what I'm going to do to the two half reactions that I care about. So we're going to rerun this calculation. I'm going to come up with the reduction potential at the cathode, get its new number, and get the reduction potential at the anode, its new number, and we'll redo this. So our first one, so if you take minus 0.13 volts, that's the old reference, you subtract the new reference, which is a negative 0.83 volts. When you do that, you get a positive 0.70 volts. And you can do a little mental double check. Okay, and you don't necessarily need to use this formula. If you take 0.83, you have to go up 0.7 to get to that number. Okay? This is 0.7 above that new reference. Okay? So you can just do some mental math if you have strong math skills or your mind is good at that. Okay? Let's do it again for the OA. So the OA is way up high compared to the new reference. We've got to go up 0.83 to get to the 0, and then we've got to go up another 1.23. So that's something you could just add those two pieces together. Or if you like a formula, take the old reduction potential, subtract the new reference. 83 volts. In both cases, I'm subtracting that new reference. So I'm taking the one in the table and subtracting the new one. And when you do this, okay, those are both negatives, so they'll both be positives. You get 2.06 volts, which is the 0.83 and then the 1.23. So we figured out the two new reduction potentials. They're 2.06 and they're 0.7. So let's see what we get as a cell potential with these new voltages. So the top one was 2.06 volts, the cathode dichromate. Okay. So we take the reduction potential at the cathode minus the anode. That was now a positive 0.7 volts. You do the subtraction, and you're fascinated. It's the exact same voltage. Didn't matter. And that's an important thing to realize. The choice of the reference doesn't matter when we calculate voltages. And it shouldn't matter. If we picked a different reference, you're not going to go in the lab and get a different voltage when you connect the cell together. The reference doesn't matter to the difference. The same way, if you change 0 degrees Celsius to a different reference, a temperature change would still be the same temperature change. Okay? Picking the reference is irrelevant. Okay? You can use degrees Celsius, which has one reference. You can use Kelvin, which has a different reference, but the change in temperature isn't affected. So kind of wrapping up this slide, you've got to watch out for one of two questions on a diploma, and potentially from me. I know what I'm going to do. I don't know what the diploma is going to do, so I have to prepare you for both. If they ask you about the voltage of the cell with a new reference, you don't care. Don't do it the new way. Okay? So if they ask you for the green version, why bother changing all those references and making a mistake? Just do it without changing the reference. It doesn't matter. If they ask you what is the reduction potential of a half reaction with a new reference, that's the green numbers and they're different. for the two pieces. You've got to recalculate those. You've got to take the number in the table and subtract whatever the new reference is, and that will re-zero everything. Okay. So watch for those two. I will put it on your assessments, and I expect this to be a diploma question. Okay. So that's the first example I wanted to go through, a bit longer one, changing the reference. The second question I'm going to do, it's going to be a lot faster. This is actually an old diploma question from 7 or 8 years ago. They gave a scandium-copper cell, so you have to realize, okay, you got scandium metal, scandium ion, copper metal. And the voltage of this scandium cell is told in the question. It's 2.36 volts. When the positive connection of the voltmeter, that was typically a red wire, is connected to the copper. And then the question was, what is the reduction potential of the scandium half reaction? So when you have a question about reduction potentials and you're given cell potential, a good strategy before you even start decoding the question, just remember E0 cell is the reduction at the cathode minus the reduction at the anode. So I'm going to get that visual out. Then I'm going to reread this question. So we've got a scandium-copper cell. Okay. Now I didn't mention this before, but the typical convention is to put the anode first and the cathode second. Okay. So that's kind of a bit of a helpful pattern that you wouldn't have seen enough examples yet to pick that up. We're told the cell potential is 2.36 volts. So that's not a reduction potential. That's what you'd see on a multimeter when you hook the two up. They're asking us what's the reduction potential of the scandium. So that's first in my cell notation and first in the standard cell vocabulary. So that's going to be our anode. So the reduction potential of the anode, we're not sure what that is. I put a question mark in. Most of you will be more comfortable when we do the math to think of that as maybe X and solve for X. So we need the reduction potential of the copper or we can't solve this, and we're okay. We got the reduction potential. That's in our data booklet. We don't have any scandium in here, so we're going to have to figure that out. We can't look it up. So where is standard copper? There's our standard copper half reaction. So that's going to be the cathode in this scandium copper cell, and that's 0.34 volts. No, I'm just going to stick in all these positives for emphasis because sometimes potentials are positive and sometimes they're negative. So we've got the cell potential, we got the reduction potential at the cathode, we have to subtract the reduction potential at the anode so we can solve for X. So I'm going to kind of skip through some of the algebra quickly. If you when you isolate for X, you'd want to bring everything to the maybe left-hand side, and then you'd have minus X, and you'd have to flip the sign. When you ultimately solve for X, you get minus 2.02 volts. So again, I didn't show all my work. Okay. For time efficiency, I'm leaving your math teachers to go through the algebra with you. And you can always double check that. Take the cathode minus, plug in that value, and you do get 2.36 volts. So that's the answer to this question. Okay. Now, a typical higher mental activity question, I see tons of these on the diploma, is could you answer a question a follow-up on scandium based on knowing its reduction potential. Okay, you should be able to take and place scandium into your table. It's not there, but we know it's at minus a little over 0.2 volts. So that would sit right there on our table. So the scandium half reaction is going to sit right where I've put that red line. Okay. The scandium metal would be on this side, and the scandium ion would be on the OA side. Now our table would tell us the most common scandium ion, and there's only one option, it's 3+. Okay. So would scandium metal react with nickel ions? Scandium metal and nickel 2 ions, yeah, they would react. The OA is above the RA. Okay? And this is an example of a higher mental activity question. Can you take some data, do something with it? And when you have to place data in a table, it typically becomes a higher mental activity skill. You have to know what to do with the data, place it, and then answer something. Okay? Now it'd be nicer if scandium was in the middle of the table. That would lead to nicer questions. So that's my two sort of bigger slides. This wraps up voltaic cells. The big thing here was being able to switch the reference. So make sure you practice that and make sure you ask me for help if you have some questions about that. We're going to stick with spontaneous cells, but we're going to leave standard conditions. Okay, so standard scandium-copper is gone. Now we're kind of into batteries. Dump in what you want. Okay, or maybe you're out in a lake. Maybe you take a piece of sodium metal and you chuck it in the lake back there, and something spontaneous happens. Okay, you chuck stuff in lakes, you're not under standard conditions. So I'm going to start with voltaic cells and pose a question. Once a voltaic cell starts to react, we lose standard conditions almost right away. So I want us to think, why are we losing standard conditions even in a voltaic cell in the lab once you've run it for a couple minutes? I'm assuming the temperature wouldn't change that much. Cells won't get hot in a minute. So it's not temperature, it's not pressure. Big issue is going to come from concentration. You pour 1 mole per liter into a voltaic cell and you start running it, that mole per liter might be getting reacted away. Might go 1 to 0.9 to 0.8 to 0.7. And once you start dropping that concentration, the voltage you get in your table won't necessarily be true. You have to be under standard conditions. That little knot we write symbol, the circle. So the measured voltage will slowly start to fall. So if you look at a time versus voltage graph, you're going to see it fairly flat, and then as the concentration drops, you'll see the voltage drop. So you don't see a big drop right away. You see a relatively flat voltage. So you take your cell phone, you charge it up, you start using it, you've got all the reactants, it's a fairly high concentration, you're going to have a steady voltage. But then over time, you'll start to see this voltage drift down, and eventually it'll kind of just fall right off. Okay. Now your cell phone is going to operate above a certain voltage. So at some point, not necessarily where that blue line ends, but your cell phone might require a voltage at that green dotted line. And once your phone voltage gets to that green dotted line, it says the battery's dead, recharge it. Your battery isn't actually totally dead, it just doesn't have enough voltage to run the electronics. So if your cell phone needs 5 volts, okay, and it starts at 6, Once it drifts under 5, it tells you it's dead. It's time to charge it back up. Okay. So kind of connecting this to the voltaic cell lab you did, any big deviation from SATP could cause your measured voltage to be different than what you would predict. So a few factors to consider. If you don't have clean electrodes, if there's all kinds of fingerprints, oils, oxidation over the electrode, you might not have a nice transfer of electrons from the electrode into probably the OA chemical that's reacting, or into whatever is in whatever electrolyte you have reacting. So if you have a barrier, that might cause you to have a lower voltage. Okay. Your salt bridge is essential to running a voltaic cell. So if your salt bridge was 1 millimeter in inside diameter, you may not have a good enough flow of ions. Or if you had a huge air bubble and your salt bridge was blocked, you have a salt bridge and you've got a huge bubble. So no ions can get across the top. Okay. So I was checking, I didn't see anybody when they did their lab having huge bubbles in that salt bridge. Okay. Last thing is impurities in solutions can cause some deviation to what you would expect. Okay. So a standard cell with silver assumes you have pure silver. You don't have anything else inside it. So big change as we go to the next slide. We're not even going to have 2 separate cells anymore. We're talking about reactions that are spontaneous but much more environmental. Okay. So corrosion is an electron transfer process. So it's an electrochemical process in which a metal, typically iron, it can be lots of different metals, but lots of industrial products are made out of iron. So when iron, which is going to be always a reducing agent, reacts with substances we find in the environment, and it forms the ionic form of iron, which is weak and flimsy, typically an orange color. Now in brackets, we have 2 common things that can cause corrosion: oxygen and or water. So what does corrosion look from a equation building perspective? So iron elemental is always going to be a reducing agent. So iron becoming iron 2 plus 2 electrons is going to be the half reaction for the oxidation. So we don't want that to happen, but if we have any OA above it, it's going to cause this. So we're going to flip to our table. What OAs could go in where that green arrow is that would cause a spontaneous reaction? Okay, so let's go to our table. Got a nice clean table. Now iron is going to be our reducing agent, elemental iron. So there's elemental iron as a reducing agent. So anything below it as an OA, we don't care about. So below this line, those would not spontaneously react with iron. Let's start at the top and identify what we might find in the environment. So fluorine, no. Lead oxide, sulfate, H+, that's actually in batteries, lead acid batteries, but hopefully you don't find that outside. No permanganate. If you find gold ions, let me know. I'll quit teaching in a hurry. Take those gold ions, make gold. So you're not going to find those. we keep going down though, oxygen and H plus potentially. You're not going to find a high concentration of H plus, but rain is naturally a little bit acidic. Oxygen's obviously in the environment, we breathe it. So that would be a possibility, even though the H plus is quite low. If we keep working our way down, no. Hopefully you don't find many nitrates. There's oxygen and H plus in a different half reaction, but the higher one up would happen first. So that one's not going, that's less spontaneous. Okay. Oxygen in water. Yeah, that's a definite. If it rains out, if it's dry, you're not going to get corrosion, but if it's damp, humid, oxygen, that's a huge one. You're going to have lots of water and lots of oxygen. Okay. Keep going down. H plus by itself. So if you have a very acidic environment, you're going to get more corrosion. If the environment's basic, you actually prevent corrosion. And that's something a student could potentially study. In hydroxides, you find you don't see much corrosion if you prevent H plus. Okay. So those are the main environmental combinations that you have to really worry about. So we had oxygen and H plus, but realize the pH would have to be really low. Okay. So a pH of 5 and a bit has like a 10 to the minus 5 concentration. Okay. Oxygen in water, if it's raining out, yeah, lots of those, or it's really humid, you're going to get lots of corrosion. H plus by itself, okay, even without oxygen, is going to cause corrosion. Again, you're going to need a high H plus concentration. So you're not going to find that super high environmentally. Okay. And then hopefully you don't find, but sulfate and H plus or nitrate and H plus is also spontaneous. Okay. But those we try not to emit in the environment. Industrial processes or companies are trying to strip out the sulfur. The oil and gas industry is trying to remove the sulfur from the gas so sulfur doesn't get released and create sulfates and create acid rain. Okay, so I didn't put the sulfates and nitrates on my list. Okay. So those are the three main ones. Last slide is how are we going to prevent corrosion? If you buy a car, you can't decide, I'm not going to drive it on the rainy days, or hopefully not, that doesn't work very well. Some people have sports cars or really nice cars, will only drive them in summer when it's dry, and they won't drive them in winter to try to make sure there's no corrosion. But we want to look at some other strategies other than avoiding any moisture. So the number one strategy to prevent corrosion, probably the simplest, is coatings. Starting off with paint. Maybe you think somebody has a red sports car and it's red because it looks cool. Well, maybe, but the number one reason for the paint is to keep the OA and the RA apart. If you have your iron in your sports car or your automobile and you have a barrier, your paint, okay, and then you've got your OAs on the outside, you've got water and oxygen, but there's a barrier between the two, that red line, and the electrons can't get from one side to the other, then there's no corrosion. And that's the goal of paints. And it's why paint chips are so bad. You have a nice vehicle, you drive it in winter, a stone chip chips some paint off, and then you have metal exposed, well, bang, there's going to be corrosion right away and rusting right away. Okay, so we've paints prevent corrosion, and then I want to talk about one other protective coating that isn't a paint, galvanizing nails. So that T is meant to be a nail, an iron nail, unprotected, and when you galvanize them, you put a zinc layer over top. So the whole nail is going to get coated. It kind of does the job of paint. But what's unique about zinc and galvanizing is when you put zinc on a nail, it will corrode, but it'll make zinc oxide, which is rock hard, like a shield. Think of like a turtle on the outside, the shell of a turtle protecting the turtle on the inside. The zinc on the outside will turn into zinc oxide, which is pretty impregnable. It's very solid. It doesn't flake off like most rust. Okay? So you get this this zinc oxide coating on the outside, and it protects the iron nail on the inside. So these are the type of nails you'd want to use in a bathroom where it could be wet, or a deck outside. Okay? You can't use iron nails outside to build a deck. The nails will corrode and your deck will shear right off your house, potentially injuring people. There's lots of YouTube videos and examples I've heard of decks breaking and shearing off houses if they're improperly built. Okay. So that's kind of the end for the coating prevention. We're going to get a little bit more scientific with cathodic protection. With cathodic protection, you attach the negative terminal to a piece of metal that you want to protect, forcing it to be a cathode. This needs to be explained a little bit more, and I'm putting up the equation that we don't want to occur. We do not want that reducing agent at an anode losing 2 electrons to become this weak, flimsy iron 2+. With hydroxide, it's that orange rusty color, hopefully everybody has seen. So we want to connect the negative terminal of a battery to our piece of iron. We want to force electrons to the iron. So if we think of our electrons are a product and we want to force this reaction to go backwards, we're going to input electrons, okay, which would drive this in reverse. Okay. And if it doesn't happen and we try to drive it in reverse, nothing is going to happen, which is good. The iron is just going to stay there. Okay. So the negative terminal to a battery will prevent the loss of electrons by forcing a gain. It won't let it lose and be the anode. It'll keep trying to have them gain, and it'll be the cathode, cathodic protection. Okay. Now, you better be a good engineer. If you are a bad engineer and you hook the wires up backwards and you put the positive terminal to the metal, you rip electrons away and you destroy it very, very quickly. And you'd be fired very, very quickly. Okay. So it's got to be that negative terminal forcing electrons to it. Okay. The last type, so this isn't cathodic protection per se, or different sub-strategy, adding another metal to become the strongest reducing agent. We're going to sacrifice something. I'll never sacrifice a student, but you can sacrifice a metal in replace of the iron. So we can add a piece of metal into our situation that's going to be stronger than iron in terms of a reducing agent. So we're going to flip to our table in a second, find iron, and see what metals would take iron's place, would be a stronger reducing agent. Okay? And then we'll come back to this slide and summarize it. So back to our table, clear our table off. There's our iron, and I don't have a lot of options to sacrifice, but I'd want to pick a metal down there. Now, I've circled things that aren't metals, but any of those metals would act as a stronger reducing agent. and only the strongest reacts. If I put in aluminum or magnesium or chromium, the iron will sit there and the other metal will react. So the sum of the metals, you don't have to write them all down, but you need to know you're looking under iron. Chemists would say any of those would work. An engineer would care about what's going to work at the right speed and what's the cheapest. What ends up being sort of the best engineering compromise is zinc. It's fairly cheap and it lasts long enough. So your Nelson chemistry textbook goes through all of corrosion and corrosion prevention in a lot more detail than I've summarized. So if you want a longer, more detailed version, I would encourage you to take a look at a few of those pages. So an example, any ship, metal, steel ship on a ocean that's salty has to really worry about corrosion. So this is a steel ocean going ship, and you'll see all these silvery pieces on the hull. They're all pieces of zinc. They'll have to be replaced every year. You don't have to cover the whole hull. You could have copper pipes or iron exposed, and it doesn't matter. You'd think, oh, everything that's going to spontaneously react with water and oxygen will corrode, but no, only the strongest reducing agent is going to corrode. So even though iron and zinc both could be exposed to the elements, the zinc corrodes and the iron doesn't. Or copper pipes are also protected by zinc. So that's a common technique used on ocean-going vessels. On fresh water, you don't have the same corrosion because you don't have a nice conductive solution.